So we're going to spend a bit of time continuing on with our Unit 2.6, Quantitative Chemistry. And you should get out your periodic table and also a calculator so that you can make sure you are working through these examples with me as we go through the booklet. So we're going to spend a little bit of time continuing on with our quantitative chemistry topic. Last week we were having a look at the difference between empirical and molecular formula. We saw how empirical formula is the simplest whole number ratio of atoms of each element in a compound, whereas the molecular formula shows us the actual number of atoms of each element in a molecule. An example of that would be ethane, as we see over in the next page. We can see that the molecular formula, the formula that gives us the actual number of atoms in the formula, is C2H6. But we can look at that ratio of atoms as 2 to 6, which we can simplify down to 1 to 3, which gets us our empirical formula of CH3. We spent a bit of time on this last week, and there are some examples in exercise 1 that you can try to have a little bit of practice in that. Over on the next page, we had a look at how you get the molecular formula from the empirical formula and the total RFM of the compound. That's essentially the mass of the molecular formula. So you can see here that my empirical formula is CH. The RFM of that empirical formula would just simply be 1 times 12 for your carbon plus 1 times 1 for your hydrogen, which is 13. The RFM of the compound, as we're told in the question, is 78. Since then the molecular formula is just a simple multiple of the empirical formula, we can work out what the molecular formula is by getting that ratio of the RFM of the molecular formula over the RFM of the empirical formula. So the RFM of our molecular formula, in other words, the RFM of the whole compound, since the molecular formula represents the actual number of atoms in our formula, divided by the RFM of the empirical formula, which is equal to 78 over 13, and that ratio is 6. We then simply get the molecular formula by taking the empirical formula and multiplying it by that ratio, which is 6. So our empirical formula was CH, we times it by 6, and that gives us C6H6. Again, over the page, in exercise 1, you have a few examples of that, and you should take some time to complete exercise 1 and get practice in these types of calculations. The next part of the topic looks at finding empirical formula using moles. In these types of questions, you will simply be given the mass of each element in a formula, or you could be given it as a percentage composition by mass. And very simply, we have 3 steps here. We have to convert our masses into moles using our equation N equals mass over RFM. And for questions that give you the masses as percentage compositions, you just have to assume that you have 100 grams. And so that means then the percentage values become values of mass. You then calculate the mole ratio by dividing all the moles by the smallest mole value. And if your mole ratio comes out as a decimal, you multiply all the mole ratios by the same number to get an integer value. That might not make a lot of sense, but we're going to look at a few examples that hopefully will help us. So if you scroll down to worked example 1, you can see that we are told in this question, in an experiment, 128 grams of copper combined with 32 grams of oxygen. What is the empirical formula of the copper oxide formed? Okay, so first of all, I'm going to write down the information I've been given under my element. Essentially, we're doing this as a ratio of copper to oxygen, and we can think of it that way as we work through. So we can see that the mass ratio is 128 grams of copper to 32 grams of oxygen. But I cannot use my mass ratio to get my formula. I must use the ratio of the number of moles. So in order to do that, I need to use the equation N equals mass over RFM. So to get that, I must have the RFM of my element. I simply look to the periodic table for that, so make sure that's out in front of you. And if we have a look at copper, it's the top number we're looking at, and we can see that it has a relative atomic mass of 64. For oxygen, the top number, the relative atomic mass, is 16. So now I'm going to convert to moles using my equation N equals mass over RFM. So if we see what that is for copper, the mass is 128, the RFM is 64, and that gives us a number of moles of 2. With oxygen, the mass is 32, the RFM is 16, so again your number of moles is 2. Take a look then back up at step number 2. We are now calculating the mole ratio by dividing all the moles by the smallest mole value. So if I look back at my question, I'm looking at my mole values. I've got 2 moles of copper and 2 moles of oxygen. So my smallest mole value is 2. So I'm dividing both of those by 2. So copper is 2 divided by 2, which is 1. Oxygen is 2 divided by 2, which is 1. Step number 3, if you look at it, just said if your mole ratio comes out as a decimal, essentially multiply it up so that it's an integer value. But we don't need to do that in this case. Our ratio is 1 to 1, which shows us that our formula is CuO. And I know you might say that we could get that by doing swap and drop with copper of a valency of 2 and oxygen of a valency of 2. But for these questions you need to work through in case the elements are in any different ratio. Worked example 2 is slightly different, so you have to just be careful about how you read the question. It says that 1.06 grams of magnesium combines with oxygen to give me 1.77 grams of magnesium oxide. So I know my mass of magnesium, it's 1.06, but my mass of oxygen is not 1.77 grams. That's the total mass of magnesium oxide that I get. So that's made up of magnesium and oxygen. So to work out your mass of oxygen that you have present, you need to do 1.77 minus your 1.06, that is your magnesium, and that gives you 0.71 grams. Okay, now we are ready to work out our number of moles. So the RFM of magnesium is 24, top number in your periodic table. Oxygen, it's 16. Calculate your number of moles now using the equation N equals mass over RFM. So for magnesium, that's 1.06 divided by 24, which gives you 0.044. Again, try to type this in your calculator as we go along. For oxygen, we are doing mass, which is 0.71, over RFM, which is 16, and that gives us a number of moles, again, of 0.044. We work out our mole ratio by dividing by the smallest number of moles. Again, in this case, it's the same for each, so the smallest number is 0.044. When we divide each of those numbers by 0.044, we're obviously dividing the number by itself, so we get a mole ratio again of 1 to 1. So my formula is simply MgO. Looking on now at worked example 3, we have an example here of a percentage composition. But as we were told back in the previous page, we just take these as the masses. We pretend that we have 100 grams. So for silicon, I have 87.5% of 100 grams. And that is obviously going to give me 87.5 grams. So we pretend we have 100 grams, so we can take the percentage compositions as masses. So you can see here that we've got silicon and we've got hydrogen. Our mass of silicon is 87.5 and our mass of hydrogen is 12.5. I need to then convert those masses into moles using my equation N equals mass over RFM. So looking at the RFM of silicon, it is 28 and the RFM of hydrogen is 1. Calculating your number of moles, you do mass over RFM. So for silicon, you've got 87.5 over 28, which gives us a number of moles of 3.125. We now do the same for hydrogen. We can see that it has a mass of 12.5 and a relative formula mass of 1. So that gives us the number of moles of 12.5. Okay, so the next step is to work out your simplest mole ratio, and we do that by dividing through by the smallest number. In this case, it is 3.125. So I'm dividing both of those numbers by 3.125. So for silicon, 3.125 divided by 3.125 is obviously going to give us 1. So that's 3.125 divided by 3.125, which gives us 1. For hydrogen, I'm doing 12.5 divided by 3.125. Put that into your calculator and you get a mole ratio of 4. So that tells us that in our formula, silicon to hydrogen ratio is 1 to 4. So my formula is SiH4. Finally, one more example to look at, and then you can try a few examples yourself. In worked example 4, it's a little bit different in that we have 3 elements, but you do it in exactly the same way. There's no difference in the method that we use. We've just got one extra element to consider, so don't be alarmed by this. So we can see here that a compound contains 4.6 grams of sodium. So we have sodium first of all, and we have 4.6 grams of it. We have 2.8 grams of nitrogen. So we'll write nitrogen up here and 2.8 grams. And then we have 9.6 grams of oxygen. So oxygen and 9.6. Again, I have to work out my number of moles, so I need my RFM. So again, look to your periodic table for this. For sodium, you can see your relative atomic mass is 23. For nitrogen, it is 14, and for oxygen it is 16. Number of moles is mass divided by RFM, so for sodium that is 4.6 divided by 23, which should give you 0.2. For nitrogen it's 2.8 divided by 14, which should give you again 0.2. And for oxygen it's 9.6 divided by 16, which gives you 0.6. Next step is to find your simplest mole ratio by dividing through by the smallest number. We can see the smallest number of moles here is 0.2, so we're dividing everything by 0.2. So that's 0.2 over 0.2, which is 1. We've got 0.2 over 0.2 for nitrogen, which is 1. And then for oxygen, we've got 0.6 divided by 0.2, which gives us 3. So the ratio of my elements for sodium to nitrogen to oxygen is 1 to 1 to 3. So that gives us an empirical formula of Na, 1 essentially, N, and then O3. What I'd like you to do now is have a go at the questions in exercise 2. They are on page 9 and also on page 10 over the page. You can make a start to those now if you have time, but what I would like you to do over Easter is complete exercise 1, which is on page 6, and that's looking at your examples of just simply writing empirical formula and then writing molecular formula from your empirical formula and your overall mass. So complete exercise 1 and exercise 2. Exercise 2 looks at determining the empirical formula from moles, and that's page 9 and 10. So if you could write that in your yearbooks now, and that is due for Thursday the 2nd of May. So you have plenty of time to get it done, but it just gives you a little bit of practice in the calculations we've done so far, so we're ready to move on the 2nd of May. You will also get given out some past papers today. I would like you to complete the questions in June 2013 and 2014. Now you'll see I have taken some questions out that were on the old specification. The moles questions will actually be from year 11 because they used to be in year 12, so you can ignore those also. I have also then put at the back of the booklet, or actually in a separate booklet I think, some electrolysis questions, as they used to be in year 11 and have now moved on to year 12. So you can take those as well, and you can be working through those at your own pace. So for the 2nd of May, I'd like you to do exercise 1, exercise 2, and those 2 papers. Enjoy! Oh, and one more thing, this video will be on YouTube. Some of you will know my channel from last year, but it's just under my name, Caroline Crawford, and I'll save it as Unit 2.6 Empirical Formula, if you want to search for it that way. Unit 2.6 Empirical Formula. If there's anything you're unsure from today, then go back, watch it again, look at the examples again before you try exercise 1 and 2.